Yes, here for Institute Colloquium given by Professor Indra from School of Physical Sciences, ISCS Kolkata. I request our team academic Professor Amita would kindly introduce.
Good afternoon and welcome to the Institute Colloquium today. It gives me great pleasure to welcome our speaker today, Professor Indra Dasgupta of the Indian Association for the Cultivation of Science. Professor Dasgupta is PhD from SN Bose National Center. From here, he is one of the first students here, and he did his PhD with Professor Abhishek Mukherjee. Then it was a postdoc at the Max Planck Institute for Solid State Research at Stuttgart in Germany, and later he was faculty at the IIT Bombay and also IIT Kharagpur before joining ISCS. His research interests are in the area of theoretical and computational condensed matter physics, including electronic structure calculation of novel magnetic systems, low-dimensional quantum spin systems, magnetic properties of materials at nanoscale and disordered systems. In addition to being a highly cited researcher, he is also an acclaimed teacher, which means you can expect a very interesting talk. We'll talk about the challenges and prospects in modeling strongly correlated systems.
There is a vibration here, right?
I think there's an echo.
No, I think there's an echo from here. Right? Just put it in luggage. এখানে রাখবো নিচে যেখানে ছিল এখানে পড়ছি পকেটে মোবাইল মোবাইল জাস্ট সিম পকেটে না থাকে ওকে that's fine. Okay, so good afternoon everybody, and
yeah, but there is an echo. I think your other mic is also on.
It's very high tech. This looks okay. So I can get started, right? So good afternoon, everybody. It's indeed a pleasure for me to be back in SN Bose National Center for Basic Sciences. Thank you, Rajiv. Thank you, Amitavo. Thank you, Manoranjan and the team, right, for the invitation to deliver the Institute Colloquium. And as I was mentioning, right, that I will assume, since this happens to the Institute Colloquium, I will assume no background, right? So basically zero background. And let's try to see what we can build up based on that. So this would be the kind of thing. And I have to give some title. So the title is Challenges and Prospects in Modeling Strongly Correlated Systems. I will essentially tell you what the challenges are, what the prospect is, and before that, I'll definitely tell you what are strongly correlated systems. Well, I think in this institute, people have been working in a variety of fields, right? So it's always a good idea to look physics at different length scales. So one of the length scale is very large, right? In units of light year. So that's where our astrophysics lives, right? A very large length scale, and possibly you can very easily go ahead and use your classical system. And then, of course, you can come to a very small length scale where the energy is very high, right? You essentially go inside the nucleus where the length scale is less than F1 meter to minus 15 meter. And that's where we do elementary particle physics and so on and so forth. But we are modest. So our length scale would be something like 0.1 nanometer. By nanometer, I mean 10 to the power minus 9 meter. So 1 angstrom to say about 1000 nanometer, right? So about 0.1 micron, right? So 0.1 nanometer to 100 nanometer. And this is the regime of condensed matter physics. And condensed matter physics can be understood both using classical mechanics, quantum mechanics, as well as a combination of the both. This is what. today's talk will primarily concentrate on so-called hard condensed matter physics. And let me also specify the length scale for you. It's something between 0.1 nanometer to 10 nanometer, where I'm solely going to use quantum physics to understand properties of the system. The kind of phenomena that I'm going to understand will essentially rely on quantum physics. So some of these things that possibly we'd like to understand are spin bulbs, right? Spin is inherently a quantum mechanical thing, and how we can manipulate spin, right? By applying either a magnetic field or an electric field, right? Where, of course, I cannot ignore quantum mechanics. Another thing is, of course, which is very popularly talked about, are topological insulators. So these in the bulk are insulators, but surface states happens to be conducting, and they have tons of applications. And these days, right, possibly I'll get some time to talk about, these days we can combine both the spin of the electron or magnetism with the topology, and where we have a kind of area which is called topological magnons and so on, right? So the talk will primarily concentrate on quantum matter, right? So this is what the idea is. So the goal is that I would like to understand quantum material. So for example, I would like to understand a magnetic material. So I have a piece of magnet, and if the length scale is greater than 100 nanometers, so what I'm alluding to is about 0.1 micron. So then this is a macroscopic continuum. So one of the ways to understand is that I take a magnifying glass, which will be able to resolve the length, right? So if I take a magnifying glass, which allows me to resolve the length between 10 to 100 nanometer, then this magnetic material will appear as a collection of atoms, and these atoms will carry spins, right? And if it happens to be a ferromagnet, the spins will conspire by some unknown mechanism to be parallel and will each be ferromagnets, right? And this aspect possibly could be understood using classical mechanics. Well, but as I told you, in this talk will be even more ambitious, right? We'd like to again use this magnifying glass and probe a length scale which is between 0.1 to 10 nanometers, right? So here, for example, I can look inside the atoms. Inside the atoms, there will be electrons, right? And these electrons will now carry spin, and these spins by some quantum mechanical mechanism, right, or exchange mechanism, is going to give me ferromagnetism or antiferromagnetism, which might finally get reflected here, right? So as I said, depending on the length scales, right, you can either use classical mechanics or quantum mechanics to understand material. And what we are going to do, we are going to use quantum mechanics to understand properties of materials, right? And as I told you, that one of the motivation here would be to understand magnetic materials, right? So for example, the simplest model that you use to describe a magnetic material is possibly a rotational invariant Heisenberg model, right? So if somebody gives you a Heisenberg model with some Jij, then you can do, for example, classical Monte Carlo simulation and, for example, get a TC for the system, right? But now if somebody tells you what is the microscopic origin of this Gij, or what is the value of this Gij, then you have to essentially go ahead and use such kind of microscopic electronic structure. Well, so the talk essentially concentrates on using quantum mechanics, right, to understand properties of a class of materials which I call quantum materials. Right? This is what the basic idea is. So let's slowly go on building up. So if I want to use quantum mechanics in understanding properties of materials, so I have to solve this Schrodinger. The simplest one is a time-independent Schrodinger equation, and this is what the Hamiltonian is. So this is the kinetic energy of the. I've only considered the electronic part of the Hamiltonian. And the simplest model for the solid, what you can think of, periodic arrangement of these ions, right? And each of these ions will liberate some free electrons, which will be moving in the solid, right? So for example, if you think of a sodium, right? So sodium will have this positive sodium core, and each sodium atom will liberate a single electron, and these electrons will interact and move around in this periodic background. So what is the Hamiltonian for this system? The Hamiltonian for this system will have kinetic energy, and this term is again, it depends on a single electronic coordinate. This is this external potential or electron-ion interaction, and this is the celebrated electron-electron interaction, right? Most difficult part. So you can see, unlike high-energy physics, we know everything about the Hamiltonian condensed matter physics, right? But still, we cannot make progress, and that's why Amitav is laughing that, right? So these guys are so lucky; they know everything, still they cannot solve, right? So something they must be having some problem. That surely they definitely have some problem. So this part, right, which depends on single electronic coordinate, is the non-interacting part, and this is of course where a pair of electronic coordinate is considered, is called an interacting part. So standard technology to solve this problem would be to map this interacting system to a system of non-interacting particles, right? Moving in some effective potential. Well, this is the standard mechanism which we learn in our first course in condensed matter physics, right? So what you do, you have this interacting system of electron, map this to a system of non-interacting electrons. But then the additional price that you pay is that these electrons are now moving in a periodic potential, right? So then you invoke your Bloch's theorem and you have this entire machinery to solve this entire thing, right? And the most systematic way this was done by, for example, using density functional theory. But there are also other methods which quantum chemists use, like Hartree and Hartree-Fock method. But density functional theory is the most popular method to use it. And what it does is reduces to an effective non-interacting system. And then you have to do a self-consistent solution of a one electron Schrodinger equation, which is very easy to do, right? I mean, and what Kohn-Sham approach provides you, Kohn-Sham approach essentially provides you or gives you a recipe to construct these potentials, right? So at the end of the day, I am supposed to solve a single particle Schrodinger equation, just like a simple harmonic oscillator problem. Except to solve, I have to do a self-consistent cycle, and the potential has a slight complication. The potential is periodic, right? So this is what my condensed matter is built on. And for such kind of systems, I know how the wave function should look like, and there is an entire machinery available. So happy state. So predictions from density functional theory of so-called local density approximation. Let's try to see. So it works. This approximation works. For example, if you have even number of electrons per unit cell, for example, in carbon, and then of course even number, because each of these bands, right, they can accommodate 2 electrons. You have even number of electrons, and if there is a band gap dictated by chemical bonding, then this band is occupied, this band is empty, and this guy is an insulator. As a consequence, your density of state is a fundamental. Well, you can have systems like calcium and strontium. Again, they have even number of electrons per unit cell, right? But what happens is that, so this, if you call this to be a valence band, the conduction band essentially overlaps the valence band. And then what you can have a metallic serum, calcium and strontium and indeed metals. Right. But for example, if you come to sodium and potassium with odd number of electrons, right? As I said, each band can accommodate only 2 electrons. If you have odd number of electrons, this band is partly occupied. So this will be a metal, and which is good for the case. So according to density functional theory, odd number of electrons per unit cell always gives rise to a metal. So the story here is that, or the kind of materials that I'm going to talk about, is that you have even number of odd number of electrons if the system happens to be an insulator. Right. So which essentially indicates the failure of band theory, and this class of systems are essentially called strongly correlated systems. So let's try to see, and where is the failure of band theory? So one of the failure of band theories, for example, cobalt oxide. So you have 9 cobalt electrons, 6 oxygen, the total number of electrons is 50. Odd number of electrons. So as a consequence, your band theory's prediction should be cobalt should be a metal. Cobalt oxide should be a metal, but cobalt oxide is the toughest insulator. Same is true for high TC cuprate lanthanum copper oxide, right? Is an insulator, has odd number of electrons, but band theory predicts it to be a metal. So this is what is the failure of single particle, where importance of electron-electron interaction has to be taken into account. Well, the situation is something like this, right? So this is what it is. That's what I have been doing. I have been essentially, I have been these electrons interacting with each other, like these cars moving in a road, right? And if the road is very broad and one car is separated from the other car, then the car can easily move, right? It doesn't care about the other car. It can move like an independent part. But if the road is narrow and you have many cars, right? So now you can see to identify any car, it cannot move in the system, right, without not being influenced by the other cars. So this is precisely what happens in a strongly correlated systems. You cannot map the problem that of a single electron moving in an effective potential, right? Right. So this explicit electron-electron interaction part has to be taken into account, right? So this is an important thing. And how do we take this into account is a challenge. We know this is my electron-electron interaction. The potential is known, but to take it in, to really make progress with this is the toughest part of the story. Well, so what one does, so one essentially again starts with this Hamiltonian, right? This is again the kinetic energy part. This is the electron-ion electron-electron interaction. Now find some complete single particle basis and represent this Hamiltonian. So then this part, right, will consist of a on-site term, a hopping term, or the so-called non-interacting part, and this is of course the interacting part. So this is the Hamiltonian in full glory, right? Just to make progress, I've identified some suitable basis and have represented the Hamiltonian in this way. Nothing beyond this I have done. And this is something which is essentially done by the quantum chemists, right? So they do this routinely. So as I told you, this model can be solved for small atoms and molecules, right? Even people who does exact diagonal, they precisely do this, right? Using quantum chemical methods, but kind of systems that we have in mind, like ITC Q-Press or anything you can think of, this is too complicated, right? So what we need to do, we have to remove degrees of freedom. So for example, you have lanthanum copper oxide, right? So if you have lanthanum orbitals, you have copper orbitals, you have oxygen orbitals. But what I will show you, close to the Fermi level where you are interested, there is only one copper D band which crosses the Fermi level, right? So in the model, I'm only going to retain that copper dx square minus y square band and forget about the rest, right? So I can integrate out these orbital degrees of freedom without compromising the physics. At the same time, this interaction is long range, right? Which is not quite necessary because in most solids, the Coulomb interaction gets screened, right? And as a consequence, I can be happy with the screened Coulomb interaction. And what often people often consider Coulomb interaction at a particular. If two electrons are a particular size, consider the Coulomb interaction, otherwise forget it. And this is the famous Aberdeen, right? So this is what I am going to do. So this is the static. So I'm not forgetting about Coulomb interaction, but I'm simplifying it depending on my requirement. Well, so as I told you, the one of the keys, so I think I have been able to convince you what do we really mean by strongly correlated systems is that I cannot map this problem to an effective single particle problem. So the first thing about a strongly correlated system, I have to explicitly take into account electron-electron interaction. And how do I do this? There are a variety of approaches, but the approach that I'm going to stick to this talk is that we are essentially going to construct a model Hamiltonian. Right? So what are the key ingredients for model Hamiltonian? This is something which I'm going to explain you carefully. For example, crystal field splitting, and what is crystal field splitting will be evident in a minute. Then, of course, electrons will hop from side to side, so kinetic hopping. This will essentially give rise to the bandwidth in the system, right? And these two things, of course, existed when I mapped the problem to a problem of a single electron moving in an effective thing. So now, explicitly, what I'm going to have, I'm going to have Coulomb interaction, and of course, cousin of this Coulomb interaction, which is this Moore's coupling. So these are the two things we are going to explicitly put in, and in addition, right, the kind of systems in which I'm going to be interested, spin orbit interaction is going to be an important part, right? So these are the four key quantities which I have to determine their relative strength. They will enter my model Hamiltonian. Once that model Hamiltonian is solved, hopefully it will give me some understanding about the physics. So the generic model Hamiltonian to start with is, of course, this single electron part, the Coulomb interaction, and of course the spin orbit coupling. So let's try to examine what this is. So crystal field and spin orbit coupling, and these are what are known as an atomic term or on-site term, right? So from where it comes, so for example, this is an example for a perovskite structure, right? So you can take it to be any perovskite you can think of where the transition metal is in an octahedral, so AbO3 kind of a thing, right? Where these are your A atoms. So for example, you can take calcium, CaMnO3. So these are calcium, and this is manganese, which is in an octahedral environment, right? So what are the active orbitals for manganese? Active orbitals for manganese are d orbitals. And we all know that d orbitals in an atom are all degenerate, right? So they are 5-fold degenerate and they can accommodate 10 electrons, right? So this is what the thing is. So now in this environment, manganese is no longer a free manganese ion, right? It is enclosed in a cage of oxygen octahedra, and this will cause a splitting, which we call crystal field splitting, right? So it will essentially break into 3-fold degenerate T2G and 2-fold degenerate Tg, and depending on the nature of hybridization, this splitting is called crystal field splitting, right? So for 3D system, it is smaller. For 5D systems, which are much more extended, it is much larger, right? We'll see. So you can see, So d orbitals are no longer 5-fold degenerate, they are 3-fold, 2-fold. So these guys can now accommodate 6 electrons, these guys can accommodate 4 electrons, and that will take care of the electron count. Well, if the system consists of a heavy material, then this T2G orbitals will also split. So this 6-fold degenerate or 6 T2G orbitals, now orbital and spin angular momentum gets entangled, right? So you have this thing. So you have in principle here, I'll mention a little later also, the 6 T2G orbitals essentially splits into 4 orbitals, which we refer to as J effective 3/2, and 2 degenerate orbitals, which we refer to as J effective 1/2, right? How this J effective 3/2 and J effective 1/2? It simply comes from L plus S and L minus S kind of things, right? So this is what we're going to see. And now you can see, so these orbitals essentially carry the information of the orbital character as well as the spin character. Well, so the point which I'm trying to make is this: these are the parameters which you can estimate from a single particle calculations like density functional theory calculation. Well, so as I told you, so we are considering this perovskite SrBO3. So it's not only a single octahedra and a single strontium atom, but you have this periodic arrangement of these atoms. And as a consequence, what you will have, the electrons will hop from side to side, and this will give rise to this band structure, right? This is what the thing is, right? And for this particular strontium vanadium oxide, what you have completely occupied oxygen 2p states. And then what you have this vanadium 3D-T2G, 3-fold T2G states, which are at the Fermi level because crystal is fixed. And then you have this vanadium EG states and higher lying strontium 4DEG and so on, right? Strontium 4D-T2G, strontium 5S, and so on and so forth, right? This is the level you have. But as I told you that when I'm going to model this, I'm not going to care about these states which are high in energy, these occupied states, but these 3 T2G states which are close to the Fermi energy, right? So if I want to construct a model, I only have these 3 active orbitals, and this is what you can see. And this we can extract out, right, by using a method called downfolding method. I'll show you a slide for this. And of course, when we are doing this, right, we are not throwing away our oxygen p orbitals or strontium d and s orbitals, right? They are somewhere denormalized, right, into this effective T2G orbitals, which defines the states close to the Fermi level. And as you can see, the effective, if you look at the effective basis of the effective 1-year function, it's no longer a pure T2G character, it has substantial oxygen characters and so on, right? So these effective orbitals essentially built up. So now if I want to construct a model, I don't talk about strontium, I don't talk about oxygen, I don't talk about vanadium EG, I only talk about 3 T2G orbitals, right? And vanadium T2G orbitals. So I can go ahead and extract this as I move along. So this is what I said from density functional theory. You can also go to minimal models, right? So what you do what is known as routine downfolding. You define active orbitals and passive orbitals. So active orbitals in this case happens to be vanadium T2G, and passive, as I pointed out, right, vanadium EG, strontium S and D, and oxygen P. And you can go ahead and partition this as active and passive orbitals, right? And then you can use this partitioning technique, right? So the eigenvalues of this Hamiltonian is identical to the eigenvalues of this Hamiltonian. So now you do a kind of simplification, this energy dependence, right? You forget about this energy dependence. And once you forget about this energy dependence, that is what you do, you essentially put this energy to be at the EF, right? So this is what you go ahead and do. Then you have this effective 3/3 Hamiltonian, where the passive orbitals, right? This passive effect of passive orbitals is included in the active orbitals, right? This is what you do, including downfolding, and you construct this effective model, right? A 3-band model, right? With which you can go ahead and work. Well, so I have been able to define at least a single electron part of the Hamiltonian, which has the on-site energy, which has the spin orbit coupling, and which also has the hopping. So this is what I have been able to do. So now I have to explicitly go ahead and define my electron-electron correlation. So what I'm going to do, so I'm essentially going to consider 2 sides, right? And each side containing 1 electron. So this is an unpaired electron. So now if I write down a Hamiltonian with a hopping, this electron merely hops to the next side. So this is what happens, and it doesn't pay any cost. And this hopping essentially reduces energy, right? Bonding and anti-bonding levels. Being 2 electrons, right, the bonding level will be occupied. So it's a state which is energetically favorable, and this precisely happens in a metal, right? So you have a DOS, and the DOS is half filled, right? So this DOS per side is half filled. As a consequence, this is the DOS for a metal. But as I pointed out, that there are 3D transition metal oxides like high TC cuprates, where the scenario is something like this, right? But this system happens to be an insulator. So what is the reason for that, right? So the reason for that is you have to add another term in the Hamiltonian, right? And what is this term? This term is this U term. What happens is that now if this electron sits in the same site, if you have a pair of electron in this site, right, then you have to essentially pay this price of this Hubbard U. And now if U is greater than T, so then this site is no longer favorable because you're paying this price for this Hubbard U, right? So what will happen? The electron will not like to hop, it will like to be localized. This U, right? What it will do, the electron will not like to sit there. Once the U is there, electron will like to be in its own site. So this motion gets arrested, right? And this, you can think of what this U does. U essentially opens up a gap, right? Now you have this state which can only accommodate 1 electron, and the for the upper Hubbard band is now separated by this factor U, right? And as a consequence, inclusion of this U drives the system to an insulator, and this is what is known as a Mott Hubbard insulator or Mott insulator, and this is your celebrated Hubbard model. Well, so you can see this minimal model, right, can now explain you insulator for odd number of electrons per site, right? So this is the important thing. Well, you can also, of course, go ahead and figure out that U is nothing but again an energy cost. You have 2 sides, each side having n electrons, right? And now what happens is that now if you transfer 1 electron from this side to this one, so then this is what the situation, and this energy difference is precisely U, and which you can also calculate. You can in fact estimate this constant energies by doing density functional theory or within random phase approximation and get an estimate. You cannot go to tell, but this U is also possible to estimate. Well, so let me go ahead and summarize now, taking the example of what? Taking the example of that cars, right, in the stream, right? So in this strongly correlated system, there are 2 energy scale. One is this hopping P, and another one is this U, right? So hopping amplitude between electrons in atom, and this is on-site repulsive interaction. As I just mentioned, what I have done, I have essentially reduced the interaction. The electrons will only interact provided they are on the same side, right? Other interactions I forget. When U is very, very less than T, like a metal system is ignorant, then your so-called band picture is okay, 1 electron per side, half filled, and you have a metal. So here, for example, broad energy bands, electrons are highly ignorant, and your independent particle picture holds good, right? This is the road is broad, and then the cars can move in this road without even caring about the other car, and that's what the story is all about. But when U is very, very greater than T, so this happens when, in the case when bands are narrow, right? So then there's a tendency for localization because electrons will start seeing each other, right? So this is an important thing. As I told you, this jam road, the cars cannot move without essentially seeing the other car, right? And this is what the so the motion of the electron is essentially blocked by this repulsion in interaction, and you have an insulating state. Well, so we talked about this effective Hubbard model, right? So for it, which has an hopping term, which has an U term, but there's also special cases when you can map an Hubbard model to a completely localized model of spins, right? For example, an Heisenberg model. When this happens when you have 1 orbital and 1 electron per side. So for example, ITC cuprates, they have 9 property electrons, right? And as you can see, these T2T levels are occupied, 3z square minus 1 level is occupied. You have only 1 electron in the copper d x square minus y square level, which ideally matches with the scenario 1 orbital and 1 electron per side. Now, what you can do when U is very, very greater than T, you take T as a perturbation, right? And what this is known as strong coupling expansion. And then you can show, and if you do this, if you take this guy as a perturbation, this thing is exact, and this guy as a perturbation, then you can show that this Hubbard model gets mapped to an Heisenberg model with this exchange coupling now being related to this hopping amplitude T and the Hubbard U, right? So if you know the T, you know the U, you can get an estimate of this Jij, and you have this Heisenberg model, right? And we all know that the parent compound lanthanum cuprate is an antiferromagnetic insulator and possibly well described by an Heisenberg model. So T, U, J, right, they can all be obtained from first principles calculation. Well, so let's make our life a little bit more complicated as we move along, right? So we talked about exchange interaction, the J, right, in our last slide, right, which that interacts by exchange interaction. If the exchange interaction is ferromagnetic, spins are parallel, and so on. But what happens to exchange interaction in the presence of spin orbit coupling, right? So this is what is spin orbit coupling, what you can have, or what is known as Dzierzhansky-Moria interaction. And there are two requirements for this. What you need spin orbit coupling, and you also need a lack of inversion symmetry, right? You have seen that your Heisenberg interaction, what was Jij, Si dot Sj, but now you have an antisymmetric exchange interaction. And what it does, it essentially favors canting of spin. So for example, if you had an antiferromagnet, right, because of this DM interaction, what will happen? The spins will get canted, right, provided there's a lack of inversion symmetry. So often people find small ferromagnetic components in an otherwise antiferromagnetic system. This happens because of this DM interaction. And as I'll show, as I move along, this DM interaction will play a key role, right, in systems where spin orbit coupling is important. Well, SOC also has a very important role. It can lead to single ion anisotropy. Heisenberg model is spherically symmetric, but SOC, for example, can tell you that you can either have an easy axis or an easy plane, right? So if there's strong enough SOC, right, you can have an easy axis. Your Heisenberg model can get mapped to a Ising model or an XY model, right? And which can be driven by SOC. So if you have system of which transition metals of heavy ions, then you can have SOC. And as I said, that Heisenberg model can be mapped to an Ising model. Ising model, of course, each one of you have studied in your condensed matter or StatMech course, right? But one can even show that the real material does behave like an Ising model. But now I'm going to talk about a very special Ising model, and this is what is known as Kitaev model, right? And I think people have talked about Kitaev model because when Kitaev did, Kitaev possibly never realized the importance of his model, right? But slowly it became obvious. So what is Kitaev model? Kitaev model is a bond directional dependent Ising coupling, which leads to exchange frustration. So this is something which I'm going to explain you in some details. Right? So for this, what you need a honeycomb lattice, right? You need a honeycomb lattice, and I think all of you are familiar with honeycomb lattice. But if you're not familiar, you just think about honeycomb lattice. If you have an atom here, it has three neighbors, right? What are these three neighbors? This is one neighbor, this is another neighbor, and this is another neighbor, and they are in 120-degree angles, right? This is what happens in a honeycomb lattice. And I guess all of you know one of the famous example of a honeycomb lattice, graphene, right? This is one of the famous example of a honeycomb lattice, right? So this is what. So now what Kitaev said. So these are. So for example, this green one he calls it as an Y bond, right? And this black one he calls this as a Z bond, and this blue one he calls it as an X bond. Okay. So I have a spin out here. I will have a spin here. I will have a spin here. I will have a spin here, right? So normal course, if this spin points along the Z direction, this spin also points along the Z direction, this spin also points along the Z direction, this spin also points along the Z direction for a normal Ising. But now what Kitaev said that if this spin points along the Z direction, the spin only along the Z bond, or so this is the Y bond, spin only along the Y bond should point along the Y direction. Right? The spin along the Y bond should point along the Y direction. Spin along the Z bond should point along the Z direction, and spin along the X bond should point along the X direction. So now you can see this guy doesn't know what to do, because along this bond he is supposed to point along the Y direction. Along this bond, this guy is supposed to point along the Z direction, and this bond, this guy is supposed to point along the X direction. So this introduces an exchange frustration. Right? So this is a special kind of an Ising model where a frustration has been introduced. Right? Well, so, and the most interesting part of this thing is that Kitaev could solve this model exactly, right? And what the ground state is, so the ground state, if the spin happens to be S equal to half on a 2D harmonic, is an exactly solvable quantum spin liquid. I will tell you in a minute what a quantum spin liquid is, but quantum spin liquids, so right, so if you see normal magnetic excitations, that they are bosons or magnons, right? But quantum spin liquids have an important property, they are fractionalized spin excitations and are topologically protected. I'll not get into gauge flux and Majorana fermions. So in fact, he essentially solved this model by using Majorana fermions. The excitations for this model are Majorana fermions, and which people thought could be used for quantum computing. Right? This is what the thing is. Well, so this model looks a very idealization, but what I'm going to tell you that there are real materials which does can be modeled by a Kitaev model. It possibly has some more terms and so on. And as so this is the phase diagram for a Kitaev model. As you can see, you can have a gapless spin liquid state, which is often referred to as Majorana metals. You can have a gap spin liquid state depending on the relative strength of your Kitaev interaction along each model. Right. So what is the proposed physical realization? So this is a work which I'm going to talk a little later. But the proposed, if you have S sharing octahedra in a honeycomb, right, with S equal to half or J equal to half Mott insulator, then you can have a bond directional Kitaev exchange. So a honeycomb material, right, where of transition metals, which forms an honeycomb material, but oxygen octahedra, where the octahedra edges share their edges, then you have a possibility of having realization of Kitaev model. So for this, what you need to do is you have to essentially cook a multi-band Hubbard model with salt. Okay. So till now I have been talking about Hubbard model with a single band and then Hubbard U, but now I'm going to generalize this. I'm going to talk about a multi-band Hubbard model, right, or a multi-orbital Hubbard model. So you have a single side but two orbitals, right? This is for the generalization now I'm going to make, right? A single side, but you have two sides, right? So if two electrons sits on the same orbital, then the energy E is equal to U, right? Which is your usual Hubbard energy. But you can also have a situation, same side, but one electron is sitting in one orbital, other electron is parallel sitting in the other orbital, which is allowed by Hund's rule. Because of this, since they are sitting on a single side, so they will have this Coulomb repulsion, which I call now U prime, or interorbital Coulomb repulsion. And since they are parallel, right, so there will lowering of energy, which I call the Hund's law, right? So this is what the thing is. If you have a pair of electrons of opposite spin, then of course you have only the repulsion term. So now let us talk about this vanadium T2G example. So I'm only going to work with 3 T2G orbitals because the system that I'm going to consider will only have 3 T2G orbitals. And matrix representation of the angular momentum for the T2G orbitals is equivalent to those of p orbitals, but with a negative sign, right? So you know the L value of a p orbital is what? L is equal to 1, and if you have S is equal to half, right? So now if you do L plus S and L minus S, then you have 3 by 2 and half. So, and 3 by 2 will have a 2S plus 1. It will have a 4-fold degeneracy, and S equal to half will have a 2-fold degeneracy, right? So these are basically your J effective 3 half and J effective half. For the T2G orbitals, your J effective half are lower, and J effective 3 half are lower, and J effective half are higher in energy, which is the reverse in the case for the T2G states. Well, so now of course my Hamiltonian becomes much more complicated, right? I have this crystal field, right, which takes care of what? This crystal field takes care of my on-site term, and this gives me the splitting between the T2G and EG, as well as if there is distortion-driven splitting in the T2G manifold. I have the hopping, right? I have the spin-orbit coupling and the interaction term. Now we'll have the usual Hubbard interaction, the inter-site Coulomb, inter-orbital Coulomb interaction, Hund's coupling, and this is known as the Kanamori Hamiltonian, right? So what I have done, I have essentially written down a model Hamiltonian, right, for 3 T2G orbitals, right, at a particular site, right, and that's essentially going to capture many of this physics. Well, so let's try to see what I can get out of this model, right? So interplay of competing parameters in 5D transition metal oxides, and the kind of 5D transition metal oxides that I'm going to consider, right? So they will have 5D electrons, right? So what is the traditional belief? Traditional belief 5D systems have large bandwidth. As a consequence, my U by T is small, right? So they are uncorrelated metals. So situation is boring. So this is what the situation. But what people have figured out, systems like calcium iridium oxide, strontium iridium oxide, sodium iridium oxide, they are all insulators. They have 5D electrons. All the 5D electrons are sitting in the T2T manifold, right? But still they are insulators. And what is the reason for that? So let us try to, these are these 5D electrons. You have this crystal field, which essentially does what? It essentially splits the T2T from the EG, and this splitting is pretty large for this 5D kind of iridates, right? This is about 2 to 3 electron volts. As a consequence, the active space happens to be this T2T space, and where these 5D electrons reside, right? As you can see, this T2T space can accommodate 6 electrons. I have 5 electrons, so system in principle should be a metal, but this guy happens to be insulated. So there comes this important thing. So now if you go ahead and apply spin orbit coupling to this, then this 6 T2T orbitals essentially splits into 4-fold degenerate J effective 3/2 and a 2-fold degenerate J effective 1/2. You have 5 electrons at your disposal. 4 electrons essentially occupy your J effective 1/2 manifold, and you have 2 orbitals and you have a single electron, right? Out here, so this is situation, right? Of a so this guys can accommodate 2 electrons. So this is precisely the situation of an half-filled Hubbard model, but now in the J effective equal to 1/2 manifold. So now if you apply a small Hubbard U, right? So this is your J effective 3/2, which is occupied. If you apply a Hubbard U, right? So then this gets occupied. So then there is a correlation induced splitting, and you have what is known as a J effective equal to 1/2 Mott insulator. ITC cuprates where S equal to 1/2 Mott insulators, right? So now you have this new paradigm with the iridates where you have to include spin orbit coupling, and you have J effective equal to 1/2 Mott insulators. So far, so good. So now, as I told you that, how can you derive a Kitaev model from this? This is the point we're just trying to tell you, right? So this is this famous paper, Mott insulator strong coupling limit, right? From Heisenberg to a quantum compass or Kitaev model. So what you do, you just, so you have this T2T states, which are split into J effective 3/2 and J effective 1/2. So you work in the spin orbital entangled J effective equal to 1/2 basis, right? You can do that, right? And as I told you, this are of course this J effective up and J effective down. They are essentially a combination of spin up and spin up orbital or particular orbital and spin down particular orbital. So these are entities like this, right, which are strongly coupled. And now you do the same thing that you did to go from Hubbard model to a Heisenberg model, right? You do the same thing. If you do the same thing, then you essentially start getting bond-dependent terms. And there is a very physical way of understanding why you get these bond-dependent terms. The reason is that now on the entities on which you are doing a strong coupling expansion, right? They not only have the information of the spin, but they also have the information about the orbitals. And you know that orbitals are very much directional. Orbitals, when they hybridize along particular direction, they don't hybridize along some other direction, right? And that essentially gives a bond directional nature, and you precisely have a Kitaev kind of an interaction. Of course, you have other interactions, but that's how you can essentially go ahead and have Kitaev interaction. So one of the requirements for Kitaev interaction is that you should, instead of having a standard Mott insulator, you should have a J effective 1/2 Mott insulator, right? In a honeycomb system, right, with H sharing octahedra. And if you have H sharing octahedra, the interesting thing is the Kitaev interaction is essentially mediated by this oxygen, and your Heisenberg interaction is mediated by this direct hopping, and which can be shown, right, because of the symmetric oxygen environment that essentially gets cancelled out, right? If you have this H sharing octahedra. So what I told you that, so what I've been alluding you to, right, starting with an electronic Hubbard model, you can map the system to a Heisenberg model, right? Again, from an electronic Kanamori model or a multiband Hubbard model, you can map it to a Kitab model, right? And both the model essentially promises exciting physics, right? So I think as I advertised that the Kitab model has this,
Right.
yeah,
This is where have to have the structure which is more like a hexagon.
honeycomb structure, right? Yeah, because Kitab is defined only on a honeycomb line. But you can also define, right? People have been, which is not, of course, in the same spirit as Kitab, but Kitab term also are present, for example, in triangular lattice. You can find Kitab term. Right.
Three birds, different
Right.
X, Y, Z.
But triangular lattices, you have 6 neighbors, but then you can, by symmetry, you can see that you can map them 3 interpenetrating kind of stuff, right? And then you can expect. Right. So does it answer your query?
Yeah.
Right. So as I told you that we are talking about, so we are basically entering a new paradigm in condensed matter physics, right? And because of spin leakage, and why I'm let me tell you why. So emergent, so as I told you, the theta model, right, essentially supports what are known as quantum spin liquids. And I did not tell you what quantum spin liquids are. So they are highly correlated quantum spins that do not order even at very low temperature, even close to 0 temperature if you're able to reach. The spins never order, right? So what one can find if you look at the exchange energy scale, right? So they are usually antiquated very large exchange energy, but they don't order down to the lowest temperature, right? And as a consequence, the frustration ratio is extremely high, right? And why this happens? This happens as a combined effect of quantum fluctuation and frustration. So now comes to the standard paradigm of condensed matter physics, what we do, right? To understand, for example, magnetism, right? We identify an order parameter. To understand superconductivity, we identify an order parameter. But you cannot have such a description out here. The Landau's theory, right? This description cannot have because you are having a state without any spontaneous symmetry breaking, right? So this is a state without any spontaneous symmetry. So you need a new machinery to understand quantum field. So this is one of the challenging aspects. And as I was trying to point out, support exotic gapped and gapless excitations. And most important features of quantum spin liquid is fractional excitations, which can be either spin-ons or Majorana fermions, and of course a quantum entanglement, right? And this quantum entanglement plays a key role in quantum computation, right? And this is something which was, of course, envisioned by Phil Anderson, right, in the year 1970, and played a very key role when he talked about ITC cuprates, right? So what you are essentially doing, you're essentially constructing. So this you can see, you're essentially constructing a singlet, right? You can see an upspin, downspin, that can be 2 linear combination of this. And what happens in the spin liquid thing, that each spin, right, dynamically interchanges its singlet partner, right, because of this entanglement. As a consequence, it can never order, right? And of course, since you don't have any spontaneous symmetry breaking, right, you need a new paradigm to understand. So this is what. Well, so if you can realize a material with Kitab interaction, and if this material happens to be a spin liquid, right, with entanglement, then of course you have a new variety of things coming up. And of course, there are topological properties associated with this stuff, right? So let me now essentially go ahead and summarize what I have been telling. Right? You have cuprates, D9, 3D orbitals where spin orbit coupling is weak. You have iridates, D5, that is 5D electrons where spin orbit coupling is strong, right? So what you have here, right? So this is what the scenario is. For cuprates, what you have, for cuprates, you have this dx square minus y square orbital, which is singly occupied, right? One hole in each spin half system. If you do a strong coupling expansion, when U is very, very greater than T, you derive your Heisenberg model. And with this model, we played around a lot, how our ladders and things, right, were essentially a kind of generalization of this. So now comes a new field, right, where you have Coulomb correlation, spin orbit coupling, which are comparable in strength. Hopping is which are comparable in strength, right? So this is what you are having a scenario like this. So here, for example, again, you have 5 electrons. You again have one hole in your J effective equal to half manifold. So instead of having in dx squared, so this is a real spin. So here you are having this pseudo spin, right? And it is again half filled. And again, you carry out this same machinery, but with exciting complicated. And here, for example, of course, you can have an Heisenberg term, but then you also have this bond directional terms or bond dependent terms out of the celebrated Kitab term.
So immediate inside. This is associated with P orbit. So
Three T2T orbitals are there, but these 3 to T2T orbitals are 6-fold linear.
So basically, because of the spin orbits.
No, not to begin with, T2T orbitals are 6-fold linear, right? So they can accommodate 6 electrons, and I have 5 electrons. So in principle, it should be a metal. Because
Spin orbital.
right, but one spin orbital interaction is 6 degenerate orbitals splits into 4-fold degenerate and a 2-fold. 4-fold degenerate gets occupied, and 2-fold degenerate now has only 1 electron. So this is what the situation is. Right? It's spin orbit coupling essentially splits into 4-fold degenerate, 2-fold degenerate. Right. So this is
Spin orbit.
Spin orbit.
Yeah.
Right. So this is what happens. So this and this. Well, passing by, I'll also talk about something which is very important and which has become very important, which is topology and magnetism. So what I have done, I've taken an Heisenberg model, right? It's a symmetric exchange interaction, and also I have taken included a DM interaction, right? So you must, I think this is also taught in your first course in condensed matter physics. If somebody gives you an Heisenberg model, right, you can essentially do a spin wave analysis, right? You do Holstein-Primakov transformation, and this model can be decoupled, right? So what I have done is that I have a Heisenberg system defined on a honeycomb lattice, right? I have a Heisenberg system defined on a honeycomb lattice, and I carry out my similar exercise of doing a Holstein-Primakov transformation. And then if you look now, what you're going to look at, you're now going to look at your Magnon bands, because there are 2 sides, A and B sides. So you have 2 Magnon branches, and these Magnon branches, interestingly, right, they just have a similar thing, just like your graphene band structure. They have Dirac cone at the K and K prime points with Magnon band. So now on top of it, if you go ahead and introduce a DM interaction, this Magnon bands, right, essentially are gapped out. If you so what you need a ferromagnetic Heisenberg model on a honeycomb lattice. It will the Magnon band structure is just like your graphene band. You include a DM interaction, bands are gapped out. They are not only gapped out, it's not only a trivial insulator. It can be shown that these guys are topological, right? So if you go and look at the surface states, so they essentially have surface states, right? So you have a Magnon band structure. I think our Magnon friend is not here, Anjan. You should be excited. Anjan plays with Magnons, right? So now you will have this surface states which are constant. He plans to do excellent. Right. Let me also tell you, so people have been contemplating that instead of this DM interaction, if you have a Kitaev interaction, then it's also supposed to get gapped out, right? So this is something which my student did a calculation. What he figured out, he of course took a when he takes, for example, a ferromagnetic Kitaev interaction, then he gets a gap like this. But if he takes an antiferromagnetic Kitaev interaction, right, so then the system never gaps out, right? So this is the point. Yes.
Yeah, but in the topological insulator, you have the surface state protected by the time reversal.
Yes.
Also,
That's a very good question. That's a very good question. So now you will say, I have a ferromagnet, how my time reversal? So what can be argued, right? You have an effective time reversal symmetry, and that essentially protects this topological state. So what I will urge you, please go and read this review by this guy, P. McClarty, right, which appeared in Quant basically when I was reading it, I precisely had this question. It's good that you asked me this question. So then there is an effective way of protecting time reversal symmetry, which protects this topological state. Perfectly well taken question. Right. So what I'm just trying to point out that if you have an Heisenberg model, ferromagnetic Heisenberg model with a DM interaction, then you can have positive topological magnons. Even with the Kitaev, you can have a positive topological magnon. Right. This is what I point out. Well, so the model that I talked about is you have this hopping term U and this spin orbit coupling. So this essentially defines 2 axes, the U axis and the lambda axis, right, which can essentially be divided into 4 parts, right? So for example, if I forget about U and lambda, then I have my simple materials, and this is the story that you learn in your Ashford-Marvin school. Well, high TC brought in this scale, right? High TC and 3D transition metal oxides, where you have this traditional Mott insulators. Well, and then of course you map it to an Heisenberg model and so on and so forth. Well, so now I think 10 years ago, this guy became very important. with the advent of topological insulator Rashba systems and so on. So you forget about U, but what you have this lambda axis, right? You have only lambda, then you can see topological and Rashba. Well, so now the most interesting part is what when you have both, right? You have spin orbit coupling as well as a Hubbard U, right? So then you can start having unconventional magnetism. Well, so I could explain you, right, the complexity of modeling things, right? So let me also see some of the prospects, and of course, as I told you, this guy can be mapped to a kind of theta model, right? So this is the paradigm in which I work, right? So we try to identify materials which falls in either of these categories, right? And then try to understand them by some means. So, right, this is what the thing is. So the idea is that this is the real material. What people usually do is that this is what the model is, right? But now if I do some guided search using the density functional theory, then my model may look slightly better. And this is what I like to do. And this compares better with this guy, right? So this is what the thing. So I will take two examples. I don't know how much time do I have, right? Maybe 5 minutes or so, right? If I have, maybe I can just talk about. So this is the work where we have been working on this honeycomb ferromagnet chromium iodide, right? So you can see chromium iodide is something where chromium sits in a honeycomb lattice, right? And what happens, and it's of course having, it enclosed in a octahedra provided by these iodines, right? Which also share cases, right? That's the point I'm trying to. So the ideal case which can happen. So this is the work which was done by two of my students, Shubhadeep. Shubhadeep is trying to finish his PhD in Belgium, and Ritik is working now in collaboration with Srin and Arun in University of Toronto, and with Kuntal Mohan and Nandini from Ohio State University, and this paper is in the archive. Well, so this is what chromium iodide is. So as I told you, so I'll not get into the structure. As I told you that the chromium is in a honeycomb lattice. Chromium is in a honeycomb lattice. It is enclosed by iodine octahedra, which essentially share their edges, right? And you can, as I told you, if this is the scenario honeycomb lattice sharing, then you have the possibility of what? You have the possibility of having a theta interaction. So it's a ferromagnet with magnetic moment 3 Bohr magneton, S equal to half. Bulk Curie temperature 61 Kelvin, ferromagnetic Curie 61 Kelvin, but they cleaves. So, and the monolayer has a temperature 45 Kelvin. It has a band gap of 1.2. I think it's a bulk band gap, so it's a Mott insulator, right? Inelastic neutron scattering experiment shows that the magnon spectra has a gap of about 4 MeV at the K point. So now try to understand. So I have a ferromagnet in a honeycomb lattice. The magnon spectra in principle is a ferromagnet. If the Heisenberg term dominates, then I should not have any gap. It should just band structure should just like here, your graphene band structure. But neutron says no. I have a 4 MeV band gap at the K point. There's also some other details we are not getting into because of lack of time. The first question is that what evades Marvin-Wagner's theorem and stabilizes ferromagnetism in a monolayer? Answer to this question is very possibly easy. That there are anisotropies, right? We essentially break the rotational symmetry of Heisenberg model, so we can take care. Right. So now, what is the origin of the gap? So this is something which people talk about. As I told you, Heisenberg model cannot open up a gap in spin wave spectra. So this is the work which Nandini Trivedi, and she essentially made me aware of this problem. They did. And they said, okay, I can explain. So don't look at these figures because we don't have time. They said that I can open up this gap seen in this neutron data, provided I have a theta interaction, which is 25 times my Heisenberg interaction. So they estimated J1 nearest neighbor Heisenberg interaction is 0.21 MeV, and theta is 5.19 MeV. Right? So this is what they said. And of course, there is this other anisotropic term, which is 0.06. So they said that if 25 times larger theta interaction opens the gap. French and Dye, so these guys are careful neutron people. They say, no, my leading scale is this nearest neighbor Heisenberg interaction, which is 2.13 MeV. But so for example, in the honeycomb lattice, as I told you, one of the requirements for DM interaction is to break the inversion symmetry. But in honeycomb lattice, the nearest neighbor, you cannot break the inversion symmetry. But the next nearest neighbor, you can break the inversion. So they said the origin of the gap is a DM interaction of 0.19 MeV, right? So this has been a debate, and this is where when Nandini made me aware of this problem and told me whether we can do something, right? This is how things went ahead. So we did a calculation. This is what Shubhadeep did, and then of course So what it figures out, so this is the inelastic neutron scattering numbers, and these are our numbers. So let's continue. So for example, the leading scale is of course the Heisenberg interaction, which is ferromagnetic. We have a sizable DM interaction, which is 0.2. Next year is our DM interaction 0.22, which compares well with the inelastic. We also get a theta interaction, but interestingly, the theta interaction is antiferromagnetic. And I already show you simulation of magnon spectra with antiferromagnetic theta interaction, which does not help in opening up a gap. And of course, there is anisotropy, and this is an easy access, right? So an anisotropy spins lots to point parallel. So this is now what we have done. So what we figure out that we then now go ahead and do the speed calculate the speed spectra. This with our parameter, this set of parameters, and you can see we can open up a gap at the K point, right? And the value of this band gap is 3 MeV, and experiment is 4 MeV. There's also a gap out here which I'm not talking about, small, but that also matches pretty well. And this is a simulation of the spin wave spectra with these guys, and they get a gap of the order of 3.5 MeV. TC for the system, 2D system, with in our simulation with this parameter turns out to 40.6 milli. This is, so I'm sorry, this should be Kelvin, and the real the TC for the experiments is 45 Kelvin, which tells us that our model is a kind of thing. And as you can see, this spectra, which can be well reproduced without theta F term, is also getting reproduced even including a theta F term, right? Even including a theta F term, but of an antiferromagnetic nature. So the understanding have been, so I don't have time. So now, of course, there are differences between these two things, and that could be essentially cured by playing with this J2 parameter. If you reduce this J2 parameter a little bit, right? So then, of course, you can go ahead and do this, right? This is what the thing is. For example, we give the J2 parameter to be 0.6 ferromagnetic, inelastic neutron scattering gets this to be antiferromagnetic. So this discrepancy, of course, exists. Well, we believe that an antiferromagnetic theta F term exists, and antiferromagnetic theta existence of antiferromagnetic theta F term can also be explained again by doing a strong coupling expansion, where your exchange promotes from T to G, T2G EG exchange path essentially promotes that via the iodine ligands, right? And which are the essential source of spin orbit coupling, right? So then what we have done, we have essentially done simulation by applying a magnetic field in the plane. And once you do that, then you can show that the TM term disappears, and then you have some signatures for the theta F term. Since I don't have time, I'm not talking about it. People who are interested, I can talk after this talk, or you can look up this preprint. Well, finally, I will talk about a realization of a theta F model in this system. Well, and we've recently done work on spin liquids, and you can also look up this review article. So this Ag3 Li-IR2O6, right? Again, it has an honeycomb lattice of iridium, right? And again, edge shearing, and the layer separations have been enhanced by essentially intercalating the silver out there. So there was a hope that these guys will be a realization of spin liquid theta F model. But what we figure out, and there had been report of this too, right? So for example, the hydrogen analog H3Li-IR2O6 has been reported to be a spin liquid by Takaki group, right? And there is also had been a paper that Ag3Li-IR2O6 happens to be this, right? So we essentially go ahead and do the same thing. We figure out that it's a J effective equal to half system, and then we find out that theta F term K by J is somewhere between 2 to 3.5, which will essentially lead to ordering, right? Because of this presence of this Heisenberg term. And this ordering, right, if you go back to the space, to the space diagram, right, either appears to be a kind of an stripy or a Neal state, right? And this is what had been predicted. And then we do a calculation, and we do find that the system happens to be a Neal state. And this is something which was also confirmed by the MUSF experiments done by my colleague in IIT Bombay, Avinash Maan. Well, so this is the story that I wanted to convey, right? So from materials to model, if you're able to identify a correct model, right, then you also identify the correct physics, right? And which also help guide you to direct experiment. Well, I think this is a strategy that we take to understand strongly for LDFS density functional theory, which gives us information about electronic structure, chemistry, as well as the structure of the system. Downfolding indicate out high energy orbital degrees of freedom plus electron-electron correlation, right? At this point, you have to extract reliable parameters and construct a low energy effective model Hamiltonian, which can be a Heisenberg model or a T-type model, and then use many body techniques to solve it. Well, and this is what I think. Thank you for your attention. And
Thank you, Indra, for a very nice talk, and I hope we can take some questions. So,
surely there are.
if there are questions, please ask.
I have a question is on that you're saying. Do you have mentioned LED oxide band structure?
Hmm.
Meaning you have projected orbitals
Keep the microphone. So even in the recording, otherwise.
Strontium iridium.
I think strontium iridium oxide something.
I just saw the picture for a minute. You go and ask your question. I'm just trying to figure out.
Yeah. So I just want to understand how.
You just ask your question. I'm just. I understand.
The doubt is that how, I mean, I see the band structure before, like lower projected orbitals.
Strontium or
One of the early bands.
I think strontium vanishes. You
It-
can
it-
talk
right. That was 3D. That was 3D.
Yes.
Right.
So-
Right. Yes,
Projected
sir.
the band structure.
This one. This is of course not my calculus. This is the current number of power and
Yeah,
like
so I suppose
Just-
the top one is without the projection of the orbitals. I think not 3D.
this one. So for example, this is your full LDA calculation where you have projected out vanadium T2G orbitals, right? You just you just project out the eigenfunctions and you can see the 3D orbitals essentially cause the formula. This is precisely what happens.
Okay, and then the bottom one is.
Bottom one is that what I do is that I integrate out these degrees of freedom and these degrees of freedom and only return this part, right? So this is what I go ahead and do.
Yes. Now my doubt is why is not much difference between that
There should not be. They will basically match exactly with each other.
they should match.
They should match exactly with that. That's what has been shown. In fact, if you cannot see the black one out here, which you possibly cannot see, is the full band structure which exactly matches with it because I have used this accurate downfolding scheme. If I have not used that, then there would have been a difference.
Yeah.
Because this band is also influenced by the oxygen P states and hopefully your strontium states, right? So since you're taking them into account, they exactly match. As a consequence, you compute the hoppings and they exactly match because you can see this T2G states are not bare T2G states. These T2G states are now anti-bonded with the neighboring oxygen, right? Mediated variety of things, right? So that's the reason they exactly match.
Okay. The other question that what I have clarity. It was asking for the time reversals to break one of these magnons.
Right. So he was asking a very important question. So I mean, if you ask me, so for example, when you in a topological insulator, so you have to essentially preserve time reversal as well as inversion symmetry. These are the two requirements. Right. So now what I'm arguing for you or what I'm telling you is not me. What people are telling us is that you have a ferromagnet on a honeycomb lattice, right? And if you can model that with an Heisenberg model and look at the Magnon spectra, the Magnon spectra has Dirac cone. Okay, right. Good. So that there's nothing topological about it. Right. So now if you add a DM interaction, then this gets gapped out. Right. So now this of course can gap out. So Magnon can be a trivial insulator. It's not a trivial insulator. It has this bulk boundary correspondence because these are Chern bands. This is what the thing is. And why these are Chern bands? Because your time reversal symmetry has to be protected in the Chern band, so people can show that there's a generalized time reversal symmetry which is protected in this case, right? And what is it generalized? You have to look up that because that paper.
Yeah. My question is that top two figures what I have seen were the Magnon spectra. And the bottom one, what you showed is
No, the bottom one will let's go to that thing again. Let's go to that. Bottom one is a calculation of my student.
yeah, is it electron band structure
No,
or
no,
Magnon?
no, I'm telling. So
It's a Magnon or electron?
this is again a Magnon band structure.
So
I'm not showing a band structure here. What I'm showing is the gap.
Yes.
So the gap value, so you can see this is a gap value. If this is red, then there is no gap. If this is blue, so for example, this part of the spectra is gap, where what you have a DM interaction as well as a ferromagnetic p-type interaction out here. But for example, if you have an anti-ferromagnetic p-type interaction, this region is red. That means no gap opens up. So this is the point which I wanted to illustrate.
So this one, that
Ah,
one is
this is not electron. This is again a magnon.
magnon, right?
Ah,
For surface state, like the surface is a surface magnet.
these are surface magnons.
So
Yes.
do we really care about magnetic spectrum and surface magnet?
Otherwise, they will not be protected. No? So this is so you have to care about some generalized time reversal symmetry.
So even for surface magnet,
Really? Right. So this is what the big point is. Chairman decides.
Sorry.
Rather, I have a comment.
Of
For
course.
example, chromium iodide is ferromagnetic and it shows linear dispersion. On the other hand, chromium fluoride, which is anti-ferromagnetic, it does not show gap or linear dispersion.
Yeah.
And another thing, as you suggested, material choice. For example, you talked about the past system. That is, we have taken in two-dimensional system. In a real material, most of them are three-dimensional, and it is very hard to find that this assumption is satisfied.
So that is one of the reasons we did this Ag3Li IR206, where putting silver, which is pretty big, you can make this honeycomb layers separate out. This is one of the reasons we identified. Well, so this thing, but
Yes.
but
I-
what kills, let me tell you, because you don't only have exclusive θ terms. In most cases, there are distortions. You will have some Heisenberg terms, and also, right, this anisotropic terms. Right, it's not only the direct bond, but X bond interacting with the Y bond by this gamma terms. So
Yes,
that
yes.
also kills the spin
Yeah,
liquid
no,
character.
my point is that chromium iodide, this system is ideal because of very weak interlayering.
Absolutely.
This gives us the opportunity, as you said, even in 2Ds, that magnetic transition is very high. So this is really idealized to two-dimensional.
But here, for example, the θ terms becomes antiferromagnetic. It's not a ferromagnetic θ. So one has to think about it.
Yeah. And another thing, chromium fluoride, I saw recently,
Ah.
when it is a monolayer, it shows XY type magnetic iodide.
It may happen. Yes, it can be.
These are very interesting.
Yeah, because for chromium chloride, spin orbit coupling is much weaker, right? So which can
Much weaker.
Right.
And monolayer chromium fluoride shows XY type.
So why don't you share your results with us?
No, this is not my area. This is publishing science.
Because the single ion anisotropy, chromium iodide is just not the single ion.
You have to ask the chairman.
Exchange energy.
Chairman.
Right, so chlorine will make a difference.
No, I was just wondering about this this calculation. What kind of calculation?
This is this thing.
Oh, spin wave.
Spin wave, right? So you take this term, and do this. So this was a young student who sat and did the 4x4 matrix, he diagonalized and poor guy.
Can I answer the question? So the chromium iodide, even without θs, if they can manage to, so there are different origins of this gas.
You're right.
So experimentally, how one can prove that θs is indeed there in chromium?
Absolutely. So this is what I told you, that you have to find some time and read this paper. So when
That's in your format paper.
no, this is
So I
my
should,
paper.
I should read.
Yeah, so this is what was done. So Feng Cheng Dai, so they have now done experiments in the presence of a magnetic field. Right. If you apply an independent magnetic field, then you can in principle kill the DM term.
But they still see the gas.
No, they have not done this experiment. So now the calculation shows if there's a Kitaev term, then the gap will not be closing, right? So it will be closing in two directions, and other two directions it will open up because if there is an antiferromagnetic theta down. So this is something. So they have to do a much more.
I'm not an expert. Being neutron in presence of magnetic field.
People have done. Feng Cheng Dai has done that. It can be done.
It will be difficult. No? It is
Done. So now they are talking to each other. But this is what, in fact, after this thing came out, this guy got in touch with Nandini, and they would like to figure out whether there's real Kitaev or not. If there was a ferromagnetic Kitaev, things would have been very easy to figure out. Antiferromagnetic Kitaev, right? So you need to do experiments. But now, what is the magnitude of this magnetic field where you can see what is the strength of this Kitaev? This, of course, matters to delve this.
Any other question?
If not, let's thank the speaker again.
all useful.